In Part 5, we'll look at thermostats and controls. Our learning outcomes for Part 5 are to understand common air source heat pump control types, to learn about integrated control strategies for backup or supplemental heat, to understand control principles, and to learn about temperature setback nuances specific to cold climate air source heat pumps.
Welcome to Part 5. The most common types of heat pump controls include a remote wand similar to a TV remote control, pictured on the top left, along with a sconce-mounted air handler used with a mini split unit. A standard programmable wall thermostat on the right and the top, a smart wall thermostat pictured underneath that, and then a mobile app which is used in conjunction with a smartphone and a smart thermostat that will communicate with the smart thermostat. Now, backup heat, when it's being used along with the heat pump, can be approached in two different ways. The backup heating capacity can provide the total heat load of the home, or it can be used as supplemental capacity and operate along with the heat pump. The operation of the backup heating equipment and the heat pump can be controlled with one thermostat and therefore termed integrated control, or the thermostat can be programmed to either switch the entire load from the heat pump to the backup heating equipment at the balance point. This slide shows how the balancing point is determined, and that's at the point where the capacity of the heat pump intersects with the load line. And it's shown here where the balancing point in blue is indicated here at a temperature of 15 degrees. The load line is this gray line, and the capacity of the heat pump is shown here in orange. And you can see as the outside air temperature goes up, which is along the horizontal axis here, the capacity of the heat pump goes up. As the temperature goes down, the capacity of the heat pump begins to diminish. And in this particular case, it diminishes to a point where it can't handle the load at those temperatures below 15 degrees. And along the vertical axis on the left are BTUs. Now this should be corrected. It's really should be in increments of 5,000 BTUs per hour. This graph shows how the heat pump and backup heat equipment operate based on outside air temperature. So an outside air temperature sensor is required. The blue line shown here shows the changes in outside air temperature over a period of time. The dashed orange line indicates the balance point, and in this case with an outside air temperature of 15 degrees. So that's where the balancing point is, and this is in line with the previous slide. The shaded blue area indicates the time that the heat pump is operating, and the yellow shaded area indicates the time when the backup heating equipment is operating. With this type of control system, either the heat pump is running or the backup heating equipment is running. Frequently, the backup system is a legacy system that was worth keeping. This diagram is a representation of the backup heating system being operated as a supplemental heating system. Now they call it backup heating on the slide. It's a little confusing, but it's the backup heating system being used to supplement the heat pump. In this type of operation, the heat pump and the backup system are operating at the same time when the heat pump's capacity is not sufficient to meet the entire heat load. Note that the heat pump and the backup or supplemental system, in this case, are being operated based on indoor air temperature. The heat pump is set to operate at a set point of 70 degrees indoor air temperature, and the backup system is set to come on when the indoor temperature droops to 67 degrees Fahrenheit. The blue shaded area represents the time when the heat pump is operating, And the yellow shaded area is when the backup capacity being used as supplemental heat is operating. And the blue line here again represents the indoor air temperature. And you can see that the heat pump is operating here. It's going on and off, and the indoor air temperature is hunting just closely to the set point of 70 degrees on the thermostat. But then when the heat pump is operating at full capacity, but is still not able to meet the indoor air setting, then the backup heating system is triggered to operate. So that then operates simultaneously along with the heat pump until the indoor air temperature again reaches 70 degrees and the backup heat cuts off and the heat pump then operates by itself. So, that may be one strategy you want to use at your house, or, you may want to have a different one where it's integrated. But that would be usually when you have an integrated system, you have an outdoor air sensor, and these are smart systems. So it knows through experience, it learns when the outside air temperature goes down to a certain point. It can anticipate that and turn on the backup heat so you don't get this droop. And controlling the supplemental heat, the supplemental thermostat is usually located in the supplemental zone. It's generally controlled by its own thermostat located within the zone and can have a set point about 2 degrees below the indoor air temperature setting for the heat pump system. Now, supplemental heat is a little different than backup heat, but they tend to use it here sometimes interchangeably. But backup heat is usually a legacy system where you have the ability to heat the entire home without the heat pump. And supplemental heat is usually when it's some form of heat added to the heat production of the heat pump. This is the way that you usually control supplemental heat. So these are some control principles. Daily setback temperatures for a heat pump are recommended to be less than that of a traditional system, only about 3 degrees, as opposed to about 7 degrees for a traditional system. Deeper setbacks for both a heat pump and a traditional system for vacations are both the same, about 7 degrees. Careful examination of the technical information for third-party thermostats, such as Nest or Ecobee, is required to assure compatibility of the heat pump's control algorithms with the third party's smart thermostat. On certain heat pump models, the efficiency operating mode may revert to the standard operating mode in the event of a power outage. Monitoring energy use by the homeowner or the installer can reveal unexpected power consumption patterns that can indicate inefficient operation. The power consumption graph on the top right shows a heat pump that is cycling in an efficient manner. The graph in the bottom right shows short cycling. This slide shows normal setback temps for traditional systems on the left and the setback temperatures for heat pumps on the right. Note the difference for setbacks and the setbacks for vacation are the same. With a deeper setback on the traditional system, the savings during the setback period are potentially greater, but the recovery penalty is also larger. With a lesser setback on a heat pump system, the compressor speed is steadier and the recovery penalty is reduced, leading to an overall efficiency increase. Auxiliary strip heating. Now, this particular strip heating they're talking about here is pictured, and it's sometimes packaged inside the heat pump itself. This is not an electric baseboard heating or something outside the scope of the heat pump. Now, this is installed as an integral part of the packaged heat pump. The purpose of the lockout is to make sure that the heater's not activated when it's not needed to meet the heating load. The lockout can be triggered in one of 2 ways. It can be locked out based on the outside air temperature, where an outside air temperature is obviously required, when the outside air is typically above a range of, say, 25 to 35 degrees Fahrenheit. Another method used to lock out the resistance heat strip is by sensing the supply air temperature of the heat pump and locking out when the supply air temperature reaches a set point of about 85 degrees Fahrenheit. The strip would then reactivate when the supply air temperature falls below the set point, typically again around 85 degrees. One of the main benefits of the lockout is to prevent the activation of the resistance heat during recovery when it's not really needed. Compressor lockouts. Pictured here is a typical hermetically sealed refrigerant compressor motor assembly. The compressor lockout feature is not needed for most cold climate air source heat pumps and should be disabled in accordance with the manufacturer's guidelines. If the compressor lockout feature is used, it is typically set to lockout at a temperature below 5 degrees Fahrenheit. So when the compressor locks out, usually at the temperature, say, below 5 degrees Fahrenheit, the heat pump is disabled and the backup system takes over. And when the temperature rises above 5 degrees, then the heat pump will come back into operation.
In part 5, we saw that heat pumps can be controlled with wand-type remotes, wall thermostats, and mobile apps. We learned that an integrated control strategy has one thermostat to control the heat pump and backup or supplemental heat, either alternating between the two systems with the balance point method or running them simultaneously using the droop method. We saw that the control principles for heat pumps are different than for traditional heating, including that third-party thermostats might affect the efficiency of the heat pump, and that heat pumps should be run in the efficiency operating mode. And we learned about temperature setbacks specific to cold climate air source heat pumps, that daily setbacks shouldn't be more than 3 degrees Fahrenheit, but vacation setbacks can be deeper. And this is because system recovery can take longer with heat pumps than with traditional systems.